In the previous video, we understood the basic electrical quantities like current, voltage, power, and energy. Now, let us take the next step and understand the different types of circuit elements used in electrical networks. Let us begin with the difference between a network and a circuit. A network is simply an interconnection of electrical elements or devices. For example, if a resistor, an inductor, and a capacitor are connected together, they form a network. In general, whenever electrical elements are interconnected, the arrangement is called a network. Now, if that network provides one or more closed paths for current to flow, then it is called a circuit. If the source is connected so that the current can leave the source, pass through the elements, and return back, the network becomes a circuit. So remember, every circuit is a network, but not every network is a circuit. A network may or may not contain a closed path, but a circuit always contains at least one closed path. Circuit element. A circuit element is the mathematical model of a physical electrical device. It defines the relationship between the voltage across the element and the current flowing through it. For example, instead of studying the internal construction of a resistor, we represent it using the relationship between voltage and current. This simplified representation makes circuit analysis easier. Circuit analysis. Once these elements are connected, we need to determine the unknown voltages across them or the currents flowing through them. This process is called circuit analysis. So, in simple terms, circuit analysis means finding the voltages across or currents through the elements of a circuit. Since different circuit elements behave differently, we classify them into different categories to make circuit analysis easier. Based on their behavior, circuit elements are classified as active and passive, linear and nonlinear, bilateral and unilateral, lumped and distributed, time variant and time invariant. Now, let us understand each one. Active and passive elements. An active element can inject power into the circuit, meaning it can supply energy to other elements. Think of a power bank charging a phone. It provides energy. Similarly, batteries, generators, and operational amplifiers provide energy to the circuit, so they are active elements. A passive element cannot generate energy. It can only absorb or store energy, just like a phone which uses the energy supplied by the power bank. For example, resistors absorb energy while capacitors and inductors store energy. So, passive elements absorb or store energy while active elements are capable of supplying energy to the circuit. Next, we have independent and dependent sources. An ideal independent source provides a specified voltage or current, and its value is completely independent of other circuit elements. You can think of it like a fan running at a fixed speed. Its output remains fixed. A dependent source, also called a control source, is an active element whose voltage or current depends on some other voltage or current in the circuit. This is like an automatic fan whose speed changes with room temperature. Depending on what controls the source and what output it provides, dependent sources are classified into four types: voltage controlled voltage source, current controlled voltage source, voltage controlled current source, and current controlled current source. Next, we have linear and nonlinear elements. An element is linear if the relationship between excitation and response satisfies homogeneity and additivity. Here, excitation is nothing but input and response is nothing but output. To understand this, imagine a person earning 100 rupees per hour. If 1 hour gives 100, then 2 hours give 200. When output changes proportionally with the input, that property is called homogeneity. That means if the input is multiplied by some constant, the output is also multiplied by the same constant. Another property is additivity, which means if multiple inputs are applied, the total response equals the sum of the individual responses. If an element satisfies both homogeneity and additivity, it is called a linear element. If these conditions are not satisfied, the element is called nonlinear. For a resistor, this linear behavior appears as a straight line, that is VI characteristic passing through the origin. Bilateral and unilateral elements. A bilateral element behaves the same even if the direction of current is reversed. In other words, its voltage current relationship remains the same in both directions of current flow. Think of a two-way road where movement is allowed in both directions. Resistors, inductors, and capacitors behave similarly, so they are bilateral elements. A unilateral element behaves differently depending on the direction of current. Think of a one-way road where movement is mainly allowed in one direction. A diode behaves like that, so it is called unilateral. Lumped and distributed elements. In lumped elements, electrical properties like resistance, inductance, and capacitance are assumed to be concentrated at one point. Their physical dimensions are considered very small compared to the wavelength of operation. This is like storing water in a tank at one location. Resistors, inductors, and capacitors are treated as lumped elements. This lumped element assumption is valid when the physical size of element is much smaller than the wavelength of operation. In distributed elements, these properties are spread continuously over the entire length. This is like water spread through a long pipeline. A transmission line is an example of a distributed element. Time variant and time invariant elements. If the parameters of an element remain constant with time, it is called time invariant. For example, if a resistor maintains the same resistance value over time, it is time invariant. If the parameters such as resistance, inductance, or capacitance change with time, the element is called time variant. These classifications help us understand how different circuit elements behave, and this forms the foundation for circuit analysis.